Hello and welcome to a biology video. Today we'll be talking Unit 5.1, Homeostasis and Control. So, why do we need a communication system? Why do all multicellular organisms need to be able to communicate between cells? We need to be able to respond to changes in our environment. Both internal and external. So examples of internal changes are stuff like pH, temperature, core body temperature as opposed to outside, core body temp, water potential of blood, and obviously external changes would be like cold or weather, and there are quite a few more examples. Hot weather that you can think of that we're responding to temperature wise. We have two different types, nervous plus hormonal. So hormonal are chemical messengers. In blood, and nervous is electrical impulses on neurons. Now, this is faster but short term, whereas hormonal will be slower and long term, as the hormone needs to be secreted into the blood and then carried to the target cells, bind to receptors and cause a change. But because the change is longer lasting, then it can take it can last longer. Nervous responses are localized because they can the impulse only will reach one particular muscle or one particular effector, whereas hormonal is widespread because your hormone can bind to lots of different receptors on lots of different cells. Other examples are paracrine, which is between close cells, and autocrine is within its own cell. So it secretes a chemical that binds to receptors on its own cell, which stimulates a response within itself. What is homeostasis? Homeostasis is, and this is a key definition, maintaining a relatively stable internal environment about a set point despite a changing external environment. That's your sort of key definition for this bit. Just going to quickly highlight it, so make sure that you guys memorize that one. Maintained by negative feedback. And we'll talk about what negative feedback is. Basically, it's the process by which any change is countered. So let's say you have a change away from the optimum. It'll reach this point and then it'll return back to the optimum. Might overshoot, it might go down a bit, but it'll go back up. So it'll kind of look like a sine wave where the optimum is the dashed line. So increase will then lead to a decrease, which will then lead to an increase. So any change away from the optimum is counted. Is counted. And you have receptors to detect this change. And effectors carry out the response. So you can either go by nervous or hormonal to the effector. An example of this is glucose regulation in blood. And when glucose levels get too high, you have insulin released, and when glucose levels get too low, you have glucagon, which is released as your hormones. They're combined to cells on the liver, which cause the formation of glycogen, and that will be more talked about in the hormonal topic. The other example is positive feedback. Which is any change away from optimum is amplified. So in a graph example, you would have the change going away from the optimum and then it'll keep going up until it reaches like a maximum point. An example of this is oxytocin release. To help breastfeeding mothers. Produce milk or cervix dilation in childbirth. Thank you for watching. Next time we're going to talk about thermoregulation and endotherms and ectotherms and the responses to each. Thank you.